Now similar to the last two theorems which were related with collinearity of two vectors, here we extend that and learn two theorems related with coplanarity of three vectors, right? So out of those two, now we have the first one. This theorem states that if three vectors a bar, b bar and c bar are coplanar, then there exist scalars m, n and p, not all 0, such that ma bar plus nb bar plus pc bar is equal to 0 bar, and the converse of the above theorem is also true. So here once again we see a very similar pattern, that is instead of 2 we have 3 vectors, and if they are coplanar then there exist some scalars which we call as m, n and p, such that not all of them are 0 simultaneously, and the linear combination formed out of them is a 0 vector, right? Now here the way we assume is if three vectors are coplanar, so let us consider them as a bar, b bar and c bar. Now if three vectors are coplanar, then using one of the previous results we can definitely express one vector, say b bar, as a linear combination of the remaining two vectors, that is a bar and c bar, because we can easily construct a parallelogram, correct, like we did earlier, and we can get the respective scalar multiples as the sides of the parallelogram. So thereby b bar can be written as a linear combination of a bar and c bar. So we can write b bar is equal to some t1 a bar plus t2 c bar. So that means if you take b bar on the other side, we will have t1 a bar plus, or rather let me write b bar in sequence of letters, plus t2 c bar is equal to 0 vector, right? So here we see that clearly we have obtained one linear combination of a bar, b bar and c bar, where one of the coefficients is definitely not 0 and the linear combination is 0, right? So therefore it proves the statement. Now the converse of the statement can also be easily proven, that is out of the three scalars, let us assume arbitrarily that one of the three scalars is not 0, and hence we can express one vector as a linear combination of the remaining two, proving that they must be all lying in the same plane, right? And lastly, moving on, we have similar counterpart of the one of the previous theorems, that is here if three vectors a bar, b bar and c bar are not coplanar, then any vector r bar in space can be uniquely expressed as a linear combination of a bar, b bar and c bar as shown here, where m, n and p are the scalars. So once again we follow the similar approach, that is let us show a bar, b bar and c bar in some general method, in some general orientation. Okay. And let us consider that r bar is some vector in space. Okay, of course we can make them all originate from the same common point which we call as origin, right? Now what we can do is we can construct a solid figure, that is let's look here, can draw a parallelogram like this. So this creates a tilted cuboid, if we can say that way, whose diagonal is the vector r bar. Now what happens is I have shown a bar, b bar and c bar as yellow colored arrows or the vectors, out of which if you consider this particular side of the tilted figure, that can be definitely written as some scalar multiple of a bar, because it is lying in the same direction of a bar, Similarly, the other side as shown here can be definitely written as some another scalar multiple of b bar, because that is also collinear with b bar itself. And lastly, the third portion can be written as some scalar multiple of c bar, right? And now you see, by vector addition we can easily prove that r bar is nothing but ma bar plus mb bar plus pc bar, because see here, if I join the diagonal of the lower face, that is a base, then clearly ma bar plus nb bar gives us this particular member, right? But to that member, if we add the third vector, which is same as pc bar, then we will get r bar. So clearly we get r bar as a linear combination of a bar, b bar and c bar. And the uniqueness can also be proven in exactly similar manner as we proved the uniqueness of the theorem in which there were only two vectors, right? So we assume by saying that let there be some set of different scalars, that is not mn and p but something else, say t1, t2 and t3, which also can be expressed as a linear combination, but it turns out that they cannot be different, they have to be the same, otherwise a bar, b bar and c bar will turn out to be coplanar, which directly contradicts the given, right? So in this way we prove this theorem. Now let us remember two important points which are basically the corollaries of these theorems. Now if we have 3 points, remember it's not 3 vectors but 3 points with position vectors a bar, b bar and c bar, okay? They are collinear if and only if there exist scalars x, y, z such that not all of them are 0, such that their linear combination is 0 and the addition of all of the scalars is also 0, right? So this is a corollary or kind of a deduction from the previous theorem. And same extended to 4 points, that is 4 points with position vectors a bar, b bar, c bar and d bar are coplanar. Are you able to see the difference between this? Right? Previously when we have 3 points we talk about collinearity, whereas if we have 4 points we talk about coplanarity. So a bar, b bar, c bar and d bar are coplanar if and only if there are 4 scalars now x, y, z, w, not all of 0, such that their linear combination is 0 and the addition of themselves is also 0, right? So we can use these facts also to solve some of the sums.